Go ahead.
Okay. We just want to. Okay. So, hello everyone. It's a coincidence, strange coincidence that my lectures are always after a cyclone. Last time it devastated West Bengal, and now there is Maharashtra and other states. Hope everyone can attend the talk today. So what we are going to do today is to mostly talk about LIGO India, but I will also give you some idea of where the gravitational wave astronomy field is heading. But again, this is indicative because we don't know how it exactly what path it is going to take in the longer run. But the important message that you will probably get here is that there is a long run. Okay, so before we go to LIGO India, oh, by the way, before I start, that in the last lecture, somebody asked a question about I don't know whether the person is there or not here, about a about these mirrors here, these PR2, PR3 mirrors. And similarly, there are SR2, SR3. So I asked someone that what are the purposes of this mirror, because I knew the purpose of the PRM, that is the power recycling mirror. So it turned out that the purpose is that there has to be a minimum distance maintained between the power recycling mirror and the beam splitter, and there is not enough space in that in the cavity. So what they do in the vacuum is to just fold the beam with these other mirrors so that it can be fitted in a smaller space. But anyway, I mean, these are just the details. I mean, we should focus right now on the principles. But it is nevertheless good that somebody asked the question and then I learned something new. Okay, coming back. So in the last lecture I talked about GW 150914. That was the first detection, and then several sources, several black hole binaries have been detected after that. But one of the most important source which we detected after that was a binary neutron star merger. This is also very much relevant for LIGO India, so we'll start here. For black holes, as you know, when two black holes merge, we don't get any electromagnetic signal out of that, which makes it very difficult to have an idea that which galaxy is hosting it, because it is coming from a region which is every part which we localize. Let's say the source is localized in, let's say, 10 square degree. There are hundreds of galaxies, thousands or could be thousands of galaxies, depending on your how far you are going in those parts. In fact, Divya Rana, which is in the talk, is an expert in that. So if we could find a follow-up radiation from one of those galaxies, or from this neutron star merger, then we could identify which galaxy became bright at that point of time, and then that would tell us the host galaxy, and then we could get many other properties of the galaxy by doing spectroscopy, like the redshift, etc. And I will come to that later on. So the crucial part here is to localize the event in a very small region of the sky. This is the thing you should remember before you go to LIGO India. I'll briefly pass through what exactly happened with this source, assuming that nobody else has covered it. The thing is that when the two neutron stars merge, they create electromagnetic radiations in different stages. And initially at very high frequency, that is gamma rays, then X-rays, and then the frequency goes down. The radio emission can happen as late as like 2 weeks, 2 months. And this was observed thoroughly by different telescopes. So this is how the localization exactly happened. Now, for this particular case, we could identify the host galaxy. There are several reasons for that, and this was just a statistically. The probability of such as of locating the source is still very low, but this source was sort of favorable. It was nearby, like 40 megaparsecs and so on. So what happened is that I'll just show this animation, then you will see what is happening. First, Fermi detected in a sort of large patch, not very small, large patch of the sky. Then there is another detection in another band, and you should look at the focus on the overlaps. Then you see that, okay, I should pause the video here. You see that the localization error with Fermi and Fermi integral together was quite large, this intersection. When two LIGO detectors and the Virgo detectors did the observation, even the Virgo did not detect anything, but it was sensitive enough. So non-detection was also told us that where the source would not be, which helped us reduce the localization error, and it became very small altogether. All these observations together made it very small, and then the electromagnetic telescope could point to that region and soon figure out which of these sources there has changed the intensity over in few hour scale, and that told us that, okay, there what is the host galaxy for this event. Okay, so this gave us not just the redshift, many information, and then, okay, this is how the observation was done. You see that because this is again a global effort, because you don't see the sky in electromagnetic radiation other than radio in the daytime. Of course, all the optical telescopes had to work in coordination, and you see that this animation shows that how day and night observations were done with telescopes across the globe. And there are many Indian telescopes also which participated, 3 of them, AstroSat, which is, I'm sure you have heard about it, GMRT, and Himalayan Chandra Telescope. Yeah, okay. Move on to, okay, wait, before I start the video. So the thing is that it was already proposed that short gamma ray bursts are probably associated. So this was a gamma ray burst, and probably it was associated to neutron star mergers. This theory was there, but with this observation, it was convincingly proved. And then this animation will tell you what are the different levels of emission. So initially, as I said, hard, and then it goes to soft. Sorry. Okay, so it is not clear to me whether you could hear the audio, but if you like last 2 lectures, please feel free to write things on the chat box, and then if whenever I pause, I will try to answer the questions, and also in between I will pause to take questions. Okay, now what are the things that we learned? So this is one of the crucial things that I'm going to show now. The previous one showed that the whole model, that we have a unified model for the this kind of gamma ray burst, okay, with the neutron star mergers. Now what we are going to show is another fundamental thing, that okay, first let me play this. Also, it is important to wait, let me just can someone confirm if you can hear the audio? It's not clear. Wait. So the audio here actually showed in, if you did not hear, then please feel free to let me know. The audio here was about, first part was the gravitational wave signal converted to an audio signal, because they are in the same frequency band, it is possible. Then after the gravitational wave signal arrived, within 2 seconds, the ting sound that came, that was basically just to signify, there was no sound really, to signify when the gamma rays was observed by Fermi. That basically meant, and this source is, as I said, pretty far away, 40 megaparsec, which is, if I remember correctly, few times 10 to the 15 light seconds. So that gravitational waves and electromagnetic waves possibly originated at the same event, came within 2 seconds, signifies that the speed of gravitational waves and electromagnetic waves are same to a fractional accuracy of 1 part, or to better than 1 part in 10 to the minus 15, 10 to the 15. Okay, so this is very nice, because then we know that probably this is a very strong proof of general relativity, because general relativity predicts that gravitational waves should travel at the speed of light. This observation already gives a very convincing proof of that. Of course, there can be still corrections, that maybe the corrections in general relativity is so small that 2 seconds probably matter. Also, the 2 seconds could signify there is something unknown in the modeling of the sources, even though there are a lot of simulations which have shown that this 2 second delay is possible for the electromagnetic waves. So all kinds of fine-tuning is going on, but nevertheless, broadly, it is pretty clear that our understanding is not too bad about this part. Okay. Then we also came to know from spectroscopy at different stages of the emission, that a large fraction of the heavy elements in the universe, like gold, etc., are produced in neutron star merger events. It was a long-standing problem that people could not explain. The amount of heavy elements that we see in the universe could not be explained with Big Bang nucleosynthesis, supernova, etc. It was proposed that maybe there is something called an R process going on during the neutron star mergers, and they generate heavy elements, and that was also proved during this event. So then, what else? I mean, there is a whole bunch of signs that came out of even just a single observation, even though a single observation does not say the whole story. But why it was so important is because there is so much unknown, that even a single observation could shine a lot of light. But there is a long way to go, as we will come there. So I have already told you about the BNS-GRB connection. Then now we come to, and there are many other things like neutron star equation of state, etc. I'm not getting into that. then the whole lecture will get into that. But a crucial problem that we will address is the measurement of Hubble constant. This plot you see, which is just this green and saffron color, actually shows the error bars of Hubble constant measurement by different experiments. The green one is from CMB, Planck, and the this whatever the color is, saffron type, it's the supernova observations. You see that both are very precise measurement. They can measure Hubble constant to, let's say, a few percent. The problem is that the error bars don't match. The green and saffron do not overlap. There is a white patch in between, making this looking like sort of Indian flag. And then there is the blue part there, which is the blue curves basically show the error bar that is coming from LIGO-Virgo observation. This error bar is of course very big right now. But the hope is that as more and more observations are done, this is going to shrink and probably come somewhere here in this white region. And then, or it could say either one of these are correct, like the green one or the saffron one, or it could say that both are wrong and it is somewhere else. So this will give us this. So basically, the point is that the LIGO-Virgo measurement will give us a different handle to the Hubble constant measurement, which currently has this tension that we don't know which one is the correct value. And this was also now in ESA's website, where the Hubble constant measurements are documented, and you can see there is now a new purple line here which signifies gravitational waves. So you can see that even with one observation, even in the very early stages of this astronomy, it is creating pretty significant results. And these are the things which you can do much better with LIGO India, and I'll come to that in a moment. So this is the status right now. I have already showed you this graph that we have a bunch of binary black hole merger detection and neutron star. One neutron star, binary neutron star merger detection. And then there are more candidates. We have probably detected one more and so on. But the thing is that there are no follow-up events. We could not follow it up. So that was the problem. And the follow-up is the crucial part for LIGO India. That is another point. Okay, so now, as I said, we are in the beginning. So what is the thing to do next? And this will be the future direction. First, we have to build a network of detectors. This will make the follow-up of sources much more precise. Right now, what is happening is that the error on the sky, even with Virgo, is so large that electromagnetic telescopes are taking a while to scan those areas. And since only for one case we have detected something, it is not clear whether before the scanning is complete, something was there. Of course, there are not many binary neutron star sources anywhere, even the potential ones. So those are the ones which are likely to emit something. For black holes, if at all we expect any hint of radiation from, let's say, surrounding accretion disk or something, it will require a very precise localization and prompt localization so that immediately telescopes can point there. For neutron stars, as I said, GW0817 was too close and also oriented in such a way that we could detect it fast. But what can happen is that most of the neutron star binary neutron star mergers will not be so close, and they may not be oriented in an optimal way. So what we need is very fast localization of the source, so that the area becomes very small and all the telescopes can sort of divide out that area and scan it very fast. Okay, that is the primary goal right now. Then the next part is to improve sensitivities of the instrument and enter the third generation detectors so that we can see much farther. Right now we are seeing really a small region of the universe. I'll show you what I mean by that. Then we have to build instruments at different frequencies. Like in the summer school, you are having lectures in optical, X-ray, gamma rays, etc. We similarly in gravitational waves, we need observatories at different frequency bands. Right now, we are right in the audible range. I mean, of course, it is not audible directly, but it is in the 10 to 2 kilohertz range. We need to build detectors at other frequency bands. And the best way would be to go to space because there is no seismic vibrations, etc. Okay, the first step, of course, for us right now is LIGO India for many other significances. Now, what do we expect with all this? I already gave you an overview that we will localize the sources better, which will allow us to measure Hubble constant more precisely. We would know how these binaries have originated, how they are distributed in space. If somebody asks us how many black holes are there in the universe, we don't know right now. But this sort of many observations will give us an idea of how many are there. The exact numbers may still not come, but we'll have some sort of idea. Okay, neutron star material, what are they made of? Okay, still there is quite a huge uncertainty in that. A very important thing is test of general relativity. So as you know, science progresses by challenging the existing theories. So, and at some point, Newton's laws were challenged, we got special relativity. Newton's laws of gravitation was challenged, we got general relativity, and we have to now see whether general relativity breaks down at certain limits, or it is the ultimate theory. Either way, we have to prove that. Of course, proving something is ultimate is probably not possible in science, but we have to keep probing to higher and higher energy scales, or smaller and smaller length scale, or larger and larger length scales as well, to see if there is things based on our current understanding. And of course, there are surprises. As I told you earlier, that when electromagnetic astronomy started, people did not even know what we are going to see today, like galaxies, pulsars, all neutron stars, all these things are completely not even imagined. So there may be a whole bunch of things that will come out in this process of measuring the known ones. Okay, so now I will, and of course, these sources span the whole huge range of frequency band. The massive binaries, huge binaries are there at lower frequencies, the smaller ones at higher frequencies. Then there are different kind of stochastic backgrounds from early universe, etc. All those things are there. I briefly covered this in the first lecture. And so there are many detectors also are being planned. These black lines basically show their sort of imagined sensitivities. There is no concrete sensitivity yet because they have not yet been designed properly, but these are the sort of target sensitivities, and they are coming up all across the spectrum. So including, for example, with radio observations, we will be able to probe this 10 to the minus 9 hertz scale, which is basically like 1 year time period, and so on. Okay, so in the longer run, of course, as you know, we have sky maps in every frequency band in electromagnetic waves, starting from radio to gamma ray, this kind of maps. And we would like to make such maps in gravitational waves also. Right now, we have only few dots in this 100 hertz sort of frequency band, and they are also not persistent. So there is a very long way to go. These things, of course, in electromagnetic astronomy, these things came, these sky maps came like 400 years after Galileo. So as you can imagine, we have to wait quite a bit. And basically, this is the graphical way to say it. So that we are here with this Galileo's telescope, and we have to go this whole way. So I will pause here for questions. If you have any questions, please raise your hand. Basically about the science goals and so on for the next generation. Okay, since there is no question, then I'll move ahead. Now, so how do we Proceed. So you see this curve shows the sensitivity plots for these detectors. Right now we have the LIGO detectors, advanced LIGO detectors. We have almost reached the sensitivity, but not yet. So we are sort of here at 10 to the minus few times 10 to the minus 24 level. Okay, and the important thing to notice is that there are this initial LIGO plots which are also there, initial LIGO, initial Fargo in cyan and green. To come from that part to the black and gray one took 10 years. In fact, it involved more than 10 years of research, but 10 years to implement, 2005 to 2015. Now, for the next generation one, which are here only two are shown, Einstein Telescope, these red and blue ones, there are more proposals from the US about Cosmic Explorer, and there is another intermediate called Voyager. So those are also being explored. So all these things will take certainly more than 10 years, probably 15 years, 20 years, who knows. So these things this is the progress path right now. What are you going to do with those? And here on this plot again, you can see the Cosmic Explorer, but the Einstein Telescope one is not there. I think I should find one where all of them are together. So you see, if you consider this plot on the right hand side, we are at the, and imagine that we are at the center. And this circles kind of shows the horizon, the left hand side for binary neutron star and the right hand side for black hole. Okay, neutron star black holes are not shown here in this. And you see that this is slightly old, so this is for showing for O2, and with O3 we are better. But again, you see that most of the binaries mergers are happening at a redshift, higher redshift, about 1 or more. These yellow dots, the yellow dots densely populate this plot in that region, right? And the white dots also sort of in that similar redshift. So we have to reach there. We are in a such a small region that almost the number of sources we are detecting is actually very small. But then that requires us to improve the sensitivity by a factor of 10. And that is what you can see from the plot on the left side. So first advanced LIGO, that is sort of with this kind of orange curve, which we have not reached yet, we are nearby. The problem of reaching the sensitivity is that you design something, but there are many other noise sources which require much longer time to actually fix. I mean, it is not just doing some calculations on pen and paper. You have to actually build the instrument and see what are the things that you could not account for while doing analytical calculations or even computer simulations. Okay, so then there is a phase called A+, where the sensitivity will be further improved within LIGO. But then if we have to go to Cosmic Explorer type sensitivity, the LIGO enclosure may not be enough. We may need a much bigger detector, maybe 40 kilometers. Einstein Telescope is 10 kilometers. So these are being explored. There is the Voyager part. Voyager proposal basically says that it can fit in the LIGO 4-kilometer arms, and which will be sort of in between, but that will be much cheaper. So maybe it will be easier to build. So all those things people are considering, that what is the best way to move forward. This is a schematic diagram of Einstein Telescope. It is it's a European effort right now. It is underground, so that the surface seismic noise is smaller. Then the arm length is 10 kilometers. Then and the frequency is sort of 10 to the minus 24. So probably will be better than that. So it's of that range. Then a lot of activities are also going on to go to space. There is a LISA mission, Laser Interferometer Space Antenna, which is likely to fly in 2034. LISA Pathfinder mission was already launched and it had enormous success. the noise level was much lower than what was expected. So that mission was launched to basically to see whether the technology would be feasible in space. So it's clearly possible. And then there is a new Chinese mission also proposed in this band, but there are more missions which are being explored, space mission and other ways of ground-based detections. Okay, now I will basically move to LIGO India. The rest of the talk will be more focused on LIGO India. So coming back to the first point, I said that what are the next steps? The first thing was to create a network of detectors to localize the sources more precisely. We already have a network. So there are two LIGO detectors in the US. There's a Virgo detector. These three are the most sensitive detectors right now, and they provide a reasonable sensitivity. The geo detector, as I told you, is for mainly for development of optics and lasers, squeeze light, etc. And there is a Kagra detector which has started operating, but right now the sensitivity is low, but it will come up at some point. And there is LIGO India. So what is how exactly a network helps in localizing a source? The thing is that it is sort of like GPS satellites. If you see on the right hand side, so if you had only two satellites on the sky, and then you could, from the time delays, you could localize a source on a ring on the sky. You see that if there are only two detectors, a ring on the sky would have the same time delay from both the detectors. It is not that so let's say detector A will give you some time delay, and detector B will give you some time delay, but there will be constant on these rings. This where the ring is basically on the plane which is perpendicular to the line joining them. You draw different circles, you get different time delays, and you can move the plane around so that then it looks like asymmetric, but still as long as the plane is perpendicular to the line joining, every ring will give you basically the same time delay from one detector and same time delay from the other detector. So this is how it is. You need three detectors in order to really localize the source on the sky. It is the same for gravitational waves. However, since the gravitational wave detectors are more sensitive in one direction than the other, if we fold in that information, then what happens is that of this ring, you can throw away some part, saying that if the source was in one of those parts, we would not have detected it because the detectors are not sensitive there. So that disadvantage that detectors cannot see everywhere on the sky, we convert it to some sort of advantage in source localization. So here you can see that there are these large patches on the sky like GW17 0104, LVT 15, 10, 12, then GW 15, 12, 26. All these cases, that was the case. They are basically like a ring on the sky, but then some parts were thrown away based on the fact that detectors were not sensitive. But when three detectors operated, that happened in this plot. There are in two cases that happened. That is one for GW17 0814 and GW17 0817. Of course, it's 2017 because the Fargo started operating properly at that time. So you see that the error bar becomes much smaller. Okay, as compared to the bigger ones, these are much smaller. Even then, this yellow patch here and there are much larger than what we can get with LIGO India, and I'm going to show that plot. So even this is a pretty big patch on the sky. When you compare to the moon, for example, this will be like of the order of 10 square degrees, which will be like 20 moons or something. And you know that how big the moon is on the sky. It's a very big patch for a telescope. The telescope, if you have observed with the telescope, its field of view is much smaller. Well, there are telescopes which have been built specifically for this follow-up. Their field of view is slightly bigger, but still not enough. Okay, so we need, and also for faint sources, this can be larger. Anyway, so this is the purpose of. I'll come to that in a moment. The thing is that another comparison is for the first detection, GW 150914, you see this huge green patch. It's pretty big. So suppose Virgo was not there, but let's say LIGO India was there, then the patch would have become this small, this orange circle on orange ellipse. So as you can see, that it will be like almost 100 times compression in the localization. So that would have happened. With Virgo, it will be even smaller. Okay. So why LIGO India? Why India? That is, why we would create another detector in India? We could choose some other country. The thing is that a lot of studies happened, and it turns out that if you put a detector in India, well, there was one optimal place was in the middle of the Indian Ocean, but I think it will be very difficult to build a detector in the middle of the ocean. So one place where it could be properly done is India, and you can see that the baseline distances increase pretty significantly. If you already have a radio physics, a radio astronomy lecture, then you know that what is the meaning of a baseline. The longer the baseline, higher is the resolution. So right now, the two Hanford detectors are 10 light milliseconds away. That is 3,000 kilometers. Virgo is like 25, 26. It is like 10,000 kilometers. Yeah, something like that. Less than that. With India, here it will be 10,000 kilometers. Virgo is in between. Also, it is in a very different direction on the other side of the globe. Now, what happens is that when you add India to this existing network of Hanford, Livingston, Virgo, see there are three baselines: Hanford, Livingston, Livingston, Virgo, and Hanford, Virgo. That is what is giving all the sensitivity right now. When you add the Indian detector, you get three more baselines with larger longer baseline length. So these things together give a significant improvement in source localization. This sort of video sort of tells you that how the detector baselines will be. But if you look at the area of the localization, the area of the triangles which are made by these detectors, you can see that with Indian detector in LIGO India, in the detector, this area becomes very large. Larger the area of this triangle, the baseline triangle, smaller the localization error on the sky. If you look at Hanford, Livingston, Virgo, it is like 130 as compared to the other detector networks, which are of the order of 300, and also there are many of them. And this will tell you also much more concretely what exactly we do get in terms of source localization error. So suppose there are two detectors in Hanford, one in Livingston, one in Virgo. There is still 4 detectors, but distributed in different way. This would be, this blue bananas on the sky would tell us what would be the source localization error. This red crosses means basically the error is very large. We cannot even, these are like almost blind spots. And on the right hand side, you will see that when we add the LIGO India detector, the areas become much, much smaller. Okay, so this is the primary advantage. And then there is a paper by Bernard Schutz about the improvement of network, and then he considered many other parameters, like how the sky is covered uniformly, if the triple detection rate, that is how confidently we can detect with this thing, and many things, and then we can find more parameters for the advantage of LIGO India. Okay, there are questions, so I will just stop here to get the questions. Okay. So somebody is asking for the slides. Actually, I am not showing anything which you cannot find in the internet. All these things are there. You just do a Google search, you will find this. So it's not necessary. The next question, is there any theoretical constraint like the uncertainty principle or similar strain that we can measure? Also, what is the relation between the frequency of the gravitational waves and the strain produced? Vishwa Kanan has asked this question. Okay, let me answer this. The thing is that yes, when you draw these curves, you know that the sensitivity curves I showed. These curves are basically drawn considering those theoretical calculations. There is uncertainty, etc., or involved. The problem that happens is that in practice, things are quite far away. But then, at least for the design, you have to do that. So, so for example, for the higher frequencies, you need more laser power. More laser power basically translates into higher radiation pressure on the mirror, and since there is a Poisson distribution, the radiation pressure starts fluctuating. That creates noise. So you can so there is a nice review about LIGO. You can get there are many reviews actually. You can get all those calculations in those papers. The thing is that you can translate this high frequency noise in terms of some kind of uncertainty relation, like there is an uncertainty between the amplitude and phase. Or you can write it as delta n, that's n in the counting noise, and delta phi kind of noise. So these sort of calculations are also possible, and they are used. I mean, it is an interpretation that how you exactly interpret the noise. This interpretation becomes very useful when you try to visualize something called quantum squeezing of light, because we are more interested in phase accuracy than amplitude accuracy. You can actually squeeze the uncertainty circle from phase to let's say it's a circle in phase and amplitude uncertainty. You can squeeze it along the phase direction so that the noise along the phase direction reduces and along the amplitude direction increases, and so on. But those are, I think, so there are many other lectures by specialists on this topic, and you have to probably listen to a 1 hour or 2 hour lecture just for those kind of calculations. Okay, the frequency of gravitational waves and the strain produced are the same. If you consider a binary, the frequency of the binary, the frequency of the gravitational waves emitted by a binary of, let's say, equal mass would be twice, because there is a symmetry involved, like after 180 degrees the same. But the frequency of the gravitational waves and the frequency of the strain that is received in the detector will be the same, except for the redshift factor. If the source is very far away, then you have to take care of redshift. When do we not operate only 2 detectors? Why do we not operate only 2 detectors and get the higher baseline and higher resolution for gravitational waves? I mean, at 2 different extremes of the globe. Well, I mean, it is difficult to. It's not just. Okay, so the countries have to invest and so on. It's not. It's a more complicated problem. Yes, we do want to increase the baseline length and so on. There was a detector which was planned in Australia also. So, but it involves a lot of things. It is a lot of money involved. Governments have to be interested. Scientific community has to be interested. All these things also matter. But only 2 would not work anyway. You need at least 3 to localize the source. 2 will. I mean, they will be farther away, but you would not be able to still localize anything. You need at least 3. And then that imagination that you are having, that only exactly on the opposite poles or in the, what is that called, antipodal points of the Earth, that is not going to work. So you need to somehow spread it out across the globe. So it is not that, by the way, that when the study was done, that what will be the most optimal location to place another detector, LIGO India is almost at the optimal location, just that in Indian Ocean is you cannot place a detector there. Okay, can you please refer to some startup books on gravitational waves? So, okay, so it depends on what exactly you are looking for. There is there are 2 volumes by Michael Maggiore, which is you can read about gravitational waves from that book. There is a book by Creighton and Anderson. It's a smaller book. These are all pretty, sometimes they are expensive. For about the instrument, there is a book by Peter Salson, which is one of those like highly respected books. There is a recently there was a second edition of the book. All these books are a bit expensive, and I think you should get into it once you decide that you are really going to work on gravitational waves. Otherwise, I mean, if you at this point you should get a flavor from every field of astronomy and try to decide what is your real liking and abilities. You try to match these two to get a choose the field, and then you can start reading about those. But these are some books. I mean, you can, if you search online, you will get this. Last thing, before I can move on, when gravitational waves passes through the detector, does not it create permanent phase difference in the detector due to the memory effect? Well, I mean, I mean, there are all kinds of papers. I mean, these are all second order effect. I mean, next order effect. That's very small. How to distinguish between Gaussian and non-Gaussian noise? Gaussian noise means a typical distribution. Non-Gaussian means a hell lot of possibilities, because it's infinite possibilities for non-Gaussian. I mean, these depend on the context. So one way is that you draw a histogram, and then the noise looks like Gaussian, then you know it is Gaussian. And the histogram for other kind of noise will be different. If there are glitches, for example, in new instrumental artifacts which are small, short-lived, which is one of the biggest problem in detecting gravitational waves. So those are non-Gaussian because they have a certain shape and so on. Okay, let me move on to the other parts. So far I have been here. So basically I have motivated so far that introduction of LIGO India will significantly reduce the localization error on the sky, which will enable us to follow up the sources rapidly, and that even those the follow-up is extremely important for different aspects of fundamental science. As even with one detection, we had got so much information, but we need many more detections in the next 20-30 years, so that we can confidently say how fast the universe is expanding and so on. And that will have other related effects in cosmology, that when we say that this is the real value for Hubble constant, for example, the neutron-star equation of state, etc., etc. Okay, moving on. So I think somebody already asked this question, that how do we choose the location of a detector? So for LIGO India, there were about 40 sites were surveyed. They were sort of, so these are dependent on many factors, but let's say that essentially the surveys were done in those places which are sort of seismically, where the seismic activities are sort of low. Even though earthquakes are sort of different from seismic activities, and this map is sort of showing the earthquake probabilities, but still you want to build a detector where the earthquakes are low. The actual thing we want is that not the earthquake part, but the ground noise should be low in general for all the time. I mean, not just during the earthquake or not. Even if there are a few earthquakes, not every year, like let's say every year, it should be fine. So finally, one site in Maharashtra was identified as the first choice. So the choices are many things has to be considered. That the sites are better. Sites should not be very close to the sea, because the sea waves create a microseismic vibrations which can scale up to come up to the detector band. The detector should be far away from human activities, so that the overall ground noise is low. Daytime and nighttime noise in the LIGO detectors actually vary. But on the other hand, so it is better that they are far away from cities. But on the other hand, people have to come to the detector to do research. This is not just a industrial facility. It is a collaborative international research where people have to fix a small problem, You need a real expert in that field, and some research is involved to even identify what the problem is. So you need many people to come and work in the observatory. So it should not be too far away from an airport also. So it is like about, let's say, of the order of 50 to 100 kilometers from an airport in a relatively smaller town city is good. Like close to Mumbai is not the ideal place, you can clearly see. Um, so based on all these criteria, rainfall, wind, all those things, the seismic surveys to see how stable the ground is, one site was shortlisted, recommended. Then that is the scientific. So there are many motivations for creating a detector in India. On one hand, you see in the left hand side, there are many scientific advantages of doing LIGO India. That you can do different, it connects to different fields of astronomy, as you saw with the neutron star detection. General fundamental physics like general relativity, could be quantum gravity and other theoretical physics, if we can probe dark energy, etc. Then there are precision measurements and fundamental tests which can be done, like how precisely you can look at an object and all those quantum experiments. And then on the other side, there is quantum measurements, laser physics, vacuum technology. Everywhere the technology improves. Okay, then computing, like grid computing, LIGO's analysis has been done on grid computing for ages. Okay, so when this cloud computing concept is coming up right now, but LIGO's computers were always distributed in different locations, and people used to submit jobs, and it used to be distributed and so on. So those things were always there. So this is how astronomy directly and indirectly helps in improving technology. Astronomy itself improves technology in a significant way, which I think there should be lectures on that. People many times cannot even imagine that how fundamentally astronomy and physics helps in your life. I think this is one of the exercises that whatever you are using right now in your life have a significant contribution from astronomy and physics. In fact, the exercise could be that if you try to find out if there is anything that did not have any effect of astronomy, did not benefit from astronomy and physics research. Anyway, so this is one of the reasons why governments also want to push this kind of projects in India, and also particularly for LIGO India, the advantage is that it's a multidisciplinary field. So what happens is that people from different fields, people meaning researchers, engineers, they share a common platform and start exchanging knowledge, which can give you a much bigger, many other very important projects. This can lead to many other important projects in science as well as industry. Okay, so for example, what we are doing right now in my institution, IUCAA, is basically coordinating an activity between several IITs, ISERs, universities, research institutions, that if there is a certain expertise which somebody has, but they don't know what LIGO needs, and we know what LIGO needs with the expertise which are available, then we do kind of a matchmaking to see that, okay, who can contribute where meaningfully, and it should be mutually beneficial. So things like that. So anyway, we also have this data center at IUCAA. I mean, I'm just telling you that how we help in infrastructure development and industry in many ways. So we have a more than 500 teraflops computing facility at this point, which is being used by the national and international gravitational community, because not every institute or IITs or university can afford a big cluster. So they log into our cluster and then use the facility. That is very much beneficial, because not everyone needs a big computer all the time. So whenever you need, you use somebody, log in here and then get your work done and then do something else. Okay. Now, this was done by my student Nikhil Mukund, and he was very much interested in machine learning. So he figured out there are many ways in which machine learning could be brought to LIGO. Now, of course, many people are using it, but this was 5 years back. It was pretty early stage, and he used it in different ways, which are now being used exclusively by LIGO people at the meaning LIGO. We are also LIGO, but basically people at the detector site who are running the detector in the control rooms. I did not have time to get into this, but all I wanted to say is that there are a lot of scope. If you are good in one thing and you don't know how that can help in this kind of projects, then you could contact us. Okay, I will end here. So gravitational waves, this is the summary. This is a take-home message, basically. As I said that everything which I said are available online. You just do a Google search based on your interest and you will get much more information than I have given you. So gravitational waves have been detected, and this is a new era in astronomy has just started. It's a long way to go. A new wind of astronomy not only provides a better picture of the universe, that we already knew something and we get a higher resolution picture of that object and or more details. It's not like that. It actually changes the whole understanding of the universe. If you see radio, X-ray, etc., and often leads to paradigm shifts. That is, a dramatic changes happen. And worldwide effort is going on to develop new detectors, new analysis strategies, new signal models, a variety of things. At present, the advanced and future detector designs, advanced detectors implementation and future detector designs are progressing pretty rapidly, even though we have not reached the full sensitivity yet because of all these things which are much beyond just theoretical understanding. And we hope there is a in the new, and also you see that even before we could reach the target sensitivity, there was a detection. And when we reach the target sensitivity and go beyond, we hope there will be far more excitement waiting for us. And then we hope that in the next few years, there will be a detector in India, which will give us like a hands-on way to work with this. So Galileo's telescope brought a renaissance in astronomy. So we hope gravitational wave astronomy will also do that. I will okay, I'll first answer a few questions and then play a video which was made by some summer school students long time ago in Caltech, and that generally entertains people and summarizes the talk in a much better way. But I will just check what are the questions right now. Okay, I will just take the quantum gravity, etc. There are different connections people make, that how you can do a laboratory test, etc. Even the detection of primordial gravitational waves could be not just with LIGO but with multiple bands, maybe could be a proof of quantum gravity in different ways. There are papers by Lawrence Krauss, etc. I mean, these are all not exactly frozen, but there are discussions on that. How to compare? Okay, wait, let me. I will come to this question. This is the most important question. How can we be part? So, how can a student be part of this effort? I'll just come to that. There is a question by Chetna Jain. The time delay of about 1.7 seconds between gravitational waves and GRB can depend on various reasons. Is there any theory result that indicates the most dominant of this reason? Well, everyone thinks their reason is the most important reason, but there are many papers written on that. I mean, you can see that. I mean, there is already a Nature paper. Then okay, you can do a Google search to find it. If not, then you can write a mail. I will send you the papers. But for example, you can see a paper by Kunal Mule. You can search that, and then you will see that there are Nature papers which are written on this issue. There are simulations which have been done. Mansi Kalsiwal, Kunal Mule. Then there is a guy called STSVI Piran. So anyway, there are many papers you can see. Okay, let me just get into. There are more questions. Actually, you could do hand up also. How to compare gravitational detector in space on Earth? Which one is better? There is nothing like better or worse. Like there are detectors. So if somebody asks you like which detector is better, an X-ray detector or a optical detector, there is nothing like that. Both are important. The frequencies of the ground-based detectors and the space-based detectors are completely different. There is basically no overlap. So these are going to see two different kinds of things. The space-based detectors, the main focus, space-based meaning the LISA. There are other space-based detectors possible. I did not get into that in the mid frequencies like decihertz, but say LISA is going to see mostly supermassive black holes, etc. LIGO sees small black holes, stellar mass black holes. So there are two different regimes. Also, the challenges are different. Like seismic noise is the main challenge for ground-based detectors. On the other hand, for in space, the acceleration noise is the how you can make a platform stable and how to make it drag-free. That is we need free mass which can move under gravity. So nothing can touch the spacecraft. All what you have to do is to keep the mirror floating in Keplerian orbit and arrange the spacecraft in such a way that it keeps following sort of the test mass without touching it. It's a very challenging thing. Different kind of challenge. When is LIGO India planned? So the operation is expected to start in 2025, but with all these delays which are happening, it's not very clear whether it will be it will slip it a little bit here and there. But we still hope that we can make it on time. Okay, how do we get to know that the wave detected in LIGO is gravitational wave? Well, I mean, there is a model that for gravitational waves, you saw the chirp signals. When you detect a chirp-like signal in one detector, you can also estimate the masses and the time of arrival. Now, if you see a gravitational wave like signal in a detector which is 3,000 kilometers away, say, or thousands of kilometers away, which within the same time limit, let's say a maximum 10 milliseconds, because that is the maximum light travel time between the two LIGO detectors and maybe little more for the other detectors, with the same mass parameters, almost the same mass parameters, nothing will be exactly matched, then the probability that the signal is not a gravitational wave becomes extremely low. In fact, the probability are also published with the results. The probability of a detection of being created just by fluke, by noise, are typically of the order of 1 in 10,000 years. So this is that small. Okay, now I come back to this important question that how people can get involved. So when you are a student, I think the most important thing is to decide, as I keep repeating, that what is your field of what should be your field of research. If you have convinced yourself, even as a student, that you want to work on gravitational waves or want to take a flavor of it, then you should probably contact one of your faculty member in your host institute to see if they can put you in touch with someone, or you can directly apply for summer programs in different institutes or something which is run by Indigo or LIGO India. So you can go to the websites and you will see the opportunities, and then you can apply or write to the people. It may also happen that in your institute already there is someone who is sort of connected to this project, and they can also, if not, they can also contact people in this Indigo consortium or LIGO India to see how they can get involved. So these are the primary ways. And also we have an outreach team. You can go to Facebook, and you can ask a question there, and then somebody will point you to the right person. You just mention that where you are from, and so on. Okay, so there is a question by Vishal Vadal. Yeah, I answered your question earlier. Last time why interferometer in 2-3 gratings? These are not gratings, they are actually mirrors. But lastly, I realized because of light coming, one ray touched the grating. No, I answered your question. If you did not hear the answer, maybe you were not there at that time. The reason is that the primary mirror is actually the PRM. The PR2 and PR3 are there because the mirror, there are certain lengths at which the mirrors have to be placed, the cavity mirror. So what happens is that there is not enough space inside the vacuum. So those mirrors PR2, PR3 are there just to fold the ray. So that instead of a straight line, you put more mirrors so that they can take a zigzag path to maintain the same length. So it's a pretty, yeah. So that was the reason. Okay. Since there are no more questions, I think I will. Okay, I have to check one more thing, that if there are questions in the YouTube live. So let me just give me a second. I will just check that. Okay. All right. Okay. Okay, there is a question about two questions. Okay, I will just answer two questions which is probably relevant for everyone. One question is that, is there anything specific about the orientation of LIGO respect to Earth's orientation, meaning direction of? Okay, so this question is this. Okay, let me come back. Okay. About the orientation, there is nothing so special. If you take the detector and orient any way you want, you will detect the sensitivity towards different polarization basically changes. But what is done, so you can, and since you don't know the polarization initially anyway, the source could be oriented in any direction, so it does not really matter whichever way you want to put it. The thing is that, but when you are putting the next detectors, that is how two LIGO detectors were put in the US, that they were exactly aligned, even though they don't look like alike, they are at 90 degrees, but because the polarization angle here is at 45 degrees, 90 degrees essentially means the same polarization. So the reason for doing that is that you will then get almost the same signal in both the detectors, apart from the noise part, that the sensitivities may be different at different times. So that is the crucial part. Now, when you put another detector on the Earth, since you have to make it like tangential to the Earth at different parts of the globe, there is actually no way of aligning with the other two detectors. You can do this exercise with matchsticks on a globe or something like that. There is basically absolutely no way, because if there is a three-dimensional surface, you cannot align it exactly. And also the thing is that it is not necessary to align. So when two detectors are aligned, when you have only two detectors, you probably want to align, because otherwise you would not know whether what you have detected is really a gravitational wave signal or not, because two detectors should detect the same thing. But when you have multiple detectors, if you don't align, then you start getting more and more information about the actual polarization of the source, because otherwise you cannot break this polarization degeneracy. But if your detector is more parallel to the other ones, then what happens is that you get more depth for the same polarization. So basically what it means is that either way you have some advantage and some disadvantage. So the main focus that people put in when getting orienting a detector is what is the most convenient way to get the land and so on. So that is the primary, I mean, how to choose the orientation, so that you have to cut the soil the least, and things like that. So these are the, and the detectors, the detector is very long. It is 4 kilometers. So when you move it little bit, you are basically on the outer side, you are actually crossing one village after another village. I mean, if it is populated. So in one direction there could be a village, but if you move it by 5 degrees or 10 degrees, you may actually cross the whole village. Or even more. So those are the things which are of primary concern when you choose the orientation of the detector. Okay, one more question was, how sensitive is LIGO India? Okay, so the LIGO India sensitivity is going to be similar to the sensitivity of the detector at that time. So at this point, LIGO India, so there are these advanced LIGO detectors. Okay, they have not yet reached the advanced LIGO full sensitivity, but very close. These detectors are now going to be upgraded to something called this advanced plus sensitivity. If LIGO India comes online at the scheduled time, LIGO India sensitivity will be matched to those sensitivity of those detectors, those two detectors, because we are essentially following the LIGO design. There can be minor changes here and there, but broadly we will follow that design. Even in LIGO, the two detectors are not identical. So this is the overall plan. Okay, one more thing was that what kind of skills are needed to be. So like if you are a computer engineer, you can contribute in certain way, in data centers, etc., grid computing, etc. If you are a electronics engineer, then you may be able to contribute in sensor technology, control systems, etc. If you are doing lasers, then there are some things, optomechanical. I mean, there are all kinds of things. I mean, I think it is better to rather ask someone who is closely related to the field, or maybe send your CV, or if you have done some projects, whether you will be uh, whether you will be able to contribute in a meaningful way to LIGO India. And if the person tells you that, okay, you see this document, this says how you might be able to contribute, and then you read the document, you decide that whether it was good or not, and then you give up. So that is, I think, a good way to go about it. Okay, so now what I will do, I think there are no more questions, so I'll end. But before that, I was thinking that I will show the video, but rather, since this video is already there on YouTube, I will try to find if it is there, and then those who are interested can see it on your own. I will just put the link there and then end the talk. Wait, just 1 second. I have to find out the link of the video. Yeah, I have got it. Yeah. I am pasting that video on the chat box for everyone. I hope everyone can see it. So if you want, you can watch it. Once the chat is closed, then you will not be able to copy the link. So I will just wait for a few seconds and then close the call. Okay? All right. Bye.